So if I then start to get into the rules in a little bit more detail, yeah. So this is yeah, it's starting to get into detail. There are a couple of colleagues have been looking at this recently with me about the different rules for beam cross-section resistance. There are a surprising number of choices, more than you would expect and more than I realised. I think most of these were in generation 1 as well. And I suppose I tend to always be thinking about beams in buildings. I'm not thinking about bridges particularly. So really we're talking about plastic cross-section resistance with either full or partial shear connection. Things like elastic, things like non-linear, and there's two alternatives for non-linear. Depends on the class of section, structure type. Yeah, buildings. I mean, most rolled sections that you're going to be using in a composite beam in the UK are going to be class 1 or 2. If it's a fabricated section, it's probably going to be class 1 or 2 as well, which is why we're always looking at plastic. Things to do with stress strain. There are a couple of ways of dealing with it, which is my next slide. Nope, sorry. So this is looking at the fact that if you've got a beam and if you've got a beam and you're going to design it, you're going to assume you've got a plastic cross-sectional moment resistance, then you're going to assume that the steel is yielded and the concrete is compressed. If you have a beam that is slightly strange proportions, so if you've got a very shallow slab, I think it would be, and a very deep beam, you can imagine that you might get a neutral axis that's quite low down. If you get a neutral axis that's quite low down, looking at the bottom left series of strain diagrams there, or there might be stress, but if you've got a neutral axis that's low down, you're going to have to get a lot of curvature before you can fully yield the steel. And by the time you've got that amount of curvature to sufficiently yield the steel to justify its plastic resistance, you might have crushed the upper fibres of the concrete. So as a concept, you can kind of understand that, yes, if you need a lot of curvature to yield the steel, and that's then going to crush the concrete, you won't actually be able to achieve that composite plastic moment resistance. It's made particularly worse if you've got high strength steel, because then you need more strain, you need more curvature to yield the steel. So in some situations, this beta factor is used to reduce the plastic resistance of the composite section so that you can still do nice and easy and cheap and cheerful plastic design without having to think about what the actual strains are, and you just put in a bit of a reduction factor. So if we look at those two plots on the right hand side of this slide, one's for S355, the lower one is for S460, you can see that you do get a bit of a drop. But then if we think about when that would start to happen, if you had a 150 slab on a 450 beam, and I know those are slightly weird numbers, but they're the right kind of size for what you would get in a building, and it makes the maths easier. If the neutral axis was at the bottom of the slab, that would give you an x over h at 0.25, which is what the horizontal axis is. So at 0.25, your reduction factor for S355 steel is only just ducking below 1. It's about 0.97 or something. Looking at the graph there. If it was S460 steel at 0.25, you're on about 0.95 for your beta factor. So really, for most beams that you're going to get in a building, the reduction because of that phenomenon is hardly worth bothering about. So a bit of extra work and hardly any benefit. In terms of what's new in the second generation, the beta factors themselves are slightly different. S355 wasn't previously covered, and now the rules do allow for partial shear connection. It was always appreciated that qualitatively that would make it less of a problem, and now the rules do allow for that a little bit. I'm not going to even attempt to go into the detail of what this graph is showing you, but some of you will be familiar with the way that you deal with partial shear connection in working out what the moment resistance of a beam is, and that straight line which goes from A to C there is A represents the moment resistance of the bare steel element, and C represents the moment resistance of the composite with full interaction. And a conservative way of considering partial interaction is to take the straight line, which is number 6 between the two. And a change in generation 2 is that if you have this beta factor coming in, because you've got a slightly weird proportion of beam, then it caps the moment resistance as beta times MPLRD.